Hi, my name is Bernard Brault, and today I'm going to go back to second video on this Euler identity, these five fundamental constant. I saw somebody posting a video a couple of weeks ago saying, here's, the 10 most important math equations, and this one was missing, and I thought, how is that possible? So I did a first video showing that this could be used to do trigonometry identities. That was a little bit boring. Not sure this one's going to be that much more fun for most of you, but some of you might enjoy going from this equation all the way to explaining how 5G, the next generation wireless technology, actually what it's used for. Um, this is the Euler's identity. E exponent I pi plus 1 equals 0. And I here happens to be equal to the square root of minus 1. And they call this an imaginary number, which I don't think should be explained this way. If you try to think of e exponent I pi and I is imaginary number, I don't think you'll ever get anywhere because it just doesn't make sense. And I'll try to make some more sense out of it, showing it to you in a different way. And the way you need to look at complex numbers is you need to look at them as some kind of an amplitude and a phase. So the amplitude is the length that you see right there. So you have a point right here, and that point that you see right there is a point in the complex plane, and the length of this arrow, if you want, that's the amplitude that you see right there, and the angle here is the angle theta. And it turns out that this could be expressed as a complex number z equals a, which is the amplitude, exponent I theta, which is the angle. And Euler's identity says that the coordinate, the x coordinate or the real coordinate, is the cosine of that angle, and the other y or imaginary coordinate is the sine of the angle. So now, if you substitute the angle theta by some kind of something that rotates at a constant frequency, and that frequency would be omega over time. And then what you have is you have this point right here, and the point just goes around in a circle like that, and it goes at a constant rate, round and round and round. And as it goes around, right, so this is like omega t, so at t equals 0, it's a e exponent 0, which is 1. It starts right there, and after a certain amount of time, depending on the frequency, if you're going at 60 hertz, for example, you're going to spin around this thing 60 times per second. Now, if you have three of these points at 100, right, three of these points, 120 degrees apart, right, this could be like representing 60 hertz phasors for power generation. So you may have a generator, and it might have a coil right here, another coil right there, another coil right here, and these coil, and then you'd be rotating a rotor inside of a stator, and then you'd be generating three-phase AC, and the three-phase are these three angles that you see right there. And the three phases would be represented by basically three complex numbers, Z1, Z2, Z3. So that's pretty much how it works. Now, if the amplitude is a unit, right? So then you have a unit circle, then the amplitude of the complex number is always 1. So in other words, this length here is 1, and no matter how you rotate around the circle, the length of that vector is always 1, and it's just the angle that changes. And when it's only the angle that changes, we call that a phasor, right? So this is a phasor. So again, you need to look at this here as a phasor, which is like some kind of a vector, if you want, and it has a certain amplitude, which is the length of the vector, and it has a certain angle theta right there, and you can nicely express it as a to e exponent I theta and do some math with it. And it turns out that the math using this is pretty trivial. What else did I want to say about this? I think there was something else. Maybe not. Um, It'll come back to me later. All right. So now let's talk about transformations, right? So what's a transformation? A transformation is when you take a certain function, right? So you take a certain function and you transform it. So here's a box, right? You transform it, and that function becomes a different function, right? So this function here becomes, so I don't know, something else, and that's why the function f transform, and I call the transformation ft for transform of the signal. And then when we have a function over time, we call these like sometimes it's called a signal, right? So I can say a signal. So a signal would be some kind of a function over time. It's something that varies over time, and you call that a signal. And you can display this on the oscilloscope and do stuff like that. Here's a couple of examples, for example, of a transformation. So you have an equalizer, and everybody who had like a, maybe these days less so, but an old stereo system where you had like a bass, middle, treble, and you had three little dials, and you could adjust how much bass you had and how much middle frequency and how much treble. So you spoke into the device, or you played the song, or you had voice, and that would be like your function f of t, right? So that'd be your input signal, and then the transform of that, right, would be your, again, it'd be your voice, but you could, instead of a flat response, you could like increase the bass right here, crank up the bass, lower the mid, and crank up the higher frequencies, and then your voice would sound different. So this transformation there is done through, and then if you change the equalizer settings, then the transformation would be a bit different. All right. So let's talk now about linear transformation. And linear transformations are a lot simpler than the other ones, and I'll show you why. So when you have something that's a linear transformation, right, again, you have a certain first function, and maybe this is like a triangular wave like that, right? And then it transforms and transforms, let's say, into sort of something that somehow looks like a triangle, but sort of rounded off, right? And then you take another function, f2, which could be like looking like a square wave like this, right? And you transform it, and it sort of looks like a square wave, but then again, it's sort of rounded out like that, right? So if the first function transforms like this, and the second function transforms like that, what a linear transformation, if that transformation is linear, right, then it has the following very, very important property is that if you actually put the sum of two inputs, the transformation is going to be the sum of the individual transformation, right? So if you add up like a triangular and a square wave together, and who knows what that looks like, then whatever the triangle wave transforms into, and whatever the square wave transform into, the sum of the two is what a linear transformation is going to do. All right, so there's an easier way to think about linear transformation that I'm going to use here. So it's similar that if you go to the supermarket and you want to know the price of a fruit basket, right? So if you know the price, let's say of an orange, one orange, the price, and the price of an apple, and the price of a banana, and and you would assume that if you buy two apples, it's twice the price of one apple. If you buy two apples and a banana, well, it's the price of the fruit basket that you have is going to be the price of two times the price of an orange plus the price, and that's pretty trivial. Now, so that's a linear transformation. Now, if you get a volume discount, that breaks the linearity, right? So again, linear transformation is such that if you know the price of an orange, or so how the number of oranges, and then you know the price of every possible fruit basket. Of course, if you throw in a pear in there and you don't know the price of a pear, then you got a problem. Then you got to figure out, okay, so now I got something else in my basket that I don't know the price of. But in order to know the pricing of any basket, any fruit basket, you just need to know the price of each, of the components. And it turns out that the price, you can think of an orange as like some kind of a base or a vector or something like that, right? Okay, so let's talk about like something called eigenfunctions and eigenvalues, and again, why they're very important. So when you have this transformation, right, f becomes a transformed function, right? So again, that was like the example I had with triangular wave became something else. There are some special functions and or signals where if you apply a transformation, right, you will get the same function, except it'll be magnified, right? It'll be scaled up or scaled down in size. And these functions are what's called eigenfunctions. And as you can see, they're probably the simplest one you can think of, right? So you have a transformation box and you put something in, right? And what you get on the other side is exactly the same thing except it's magnified, right? So those functions would be sort of special functions if you want, and they're special because they're simple. Uh, and all you need to know about the transformation is you just need to multiply by some kind of an amplification factor, right? So a scale up factor, if you want. So here it is. So you got this special, it's not just any function, you got this special function here. And if that special function under a certain transformation scales, then we say that this function is an eigenfunction, and this is the eigenvalue, lambda here, right? So we call these function eigenfunctions. Big name for a simple thing, right? I don't know why people do that. Anyway, and the scaling factor is called the eigenvalue. So let's go back to our friend here, the phasor, right? So this again, this is like, if you remember, this is you have the unit, this is a real axis, this is imaginary axis, and this is a vector, and it's a vector on the unit circle because it's implied that the amplitude here is 1, and he has a certain angle right there, and we call that a phasor. Okay, so now I'm going to scare you because we're going to do a derivative of this thing. Okay, so but bear with me. So the transformation will be a derivative with respect to the angle. That's going to be our transformation right there. So you take a certain function, you take the derivative. Typically, you think of a derivative as a slope or whatever, you were taught in high school or college, and then you obtain a new function, right? So you take a certain function, you take the derivative of the function, and then you get something else, right? So this is, and it's a linear transformation because if you take the derivative of the sum of two functions, it's the sum of the derivatives, and if you scale it up and so on, right? So let's take a look now at our friend, the phasor, and let's take the derivative of the phasor. So if you take the derivative of e exponent ax, right? If you remember a little bit, right? If you take d over dx of that, it's a times e to the ax, right? And the nice thing about e exponent x is that the derivative of e exponent x is e exponent x, and this is by definition, and that's how Euler found this ease. He said, oh, I'm looking for a function so that the derivative is the same as a function. So the derivative of e exponent I theta of our phasor, right, is you pull out the I in front and then you multiply by e exponent I theta. So right away you see that this here, e exponent I theta, or phasor, stays the same, right? So it stays the same, except it gets multiplied by I, right? So e exponent I theta is an eigenfunction because when you of the derivative transformation, this is a transformation, and you take a derivative here and you get the same e exponent I theta multiplied by what? Multiplied by the square root of -1. Wow, this is crazy. You know what? There's no way I could explain what multiplying by the square root of -1 means. It doesn't mean anything. And if anybody teaches you that multiplying by the square root of -1 has any meaning, they just don't know what they're talking about. But there's a way to put some meaning into this, right? Remember I said never think of a imaginary number as the sum of a real thing plus a square root of -1. Always go back to phasors, right? So uh, what's I, right? So we're back to e exponent I pi right here. And I, this is 1. This is number 1 right here. And this here, right? This here is I. This, you go down there, it's -1. You go right down there, this is minus I, and you go back into 1, right? So, and it turns out that this phasor right there, which is a 90 degree, so e exponent I times 90 degree, which is pi over 2, because it just turns out that this length right here is pi over 2. Because if you go all the way around the unit circle, the length that you've walked around is 2 pi. So this is pi, this is 2 pi, and this is pi over 2. Remember, like we express angles in their natural form, which is a length. It's the length of the unit circle that you walk around. So when you think of I as being equal to e exponent I pi over 2, then I is just, it's a phasor. And it's a phasor that's got amplitude 1 and an angle of 90 degree. Right? So, okay, so what does that mean? That means that multiplying by I is shifting whatever you put in by 90 degrees. And that makes more sense, right? So let's take a look here, right? So you got a certain complex number, an arbitrary complex number, a e I pi, and you multiply by I, which is, forget about this thing, right? Which is a phasor, a 90-degree phasor, and what you end up doing is you need to add the, this plus this, right? You put things together, and math is very simple exponential rule, and you end up like taking the original function here and phase shifting it by 90 degree. So scaling or multiplying by I is just a 90-degree shift, right? So, and remember this was like the eigenvalue of a derivative of e exponent I theta, right? Um, so again, we're back here, so now it makes more sense. And this here just simply means that we're actually multiplying or shifting by 90 degree. So e exponent I theta is an eigenfunction of the derivative transformation, and I is its eigenvalue, right? So square root of minus 1, forget about that, right? What we're talking about now is simply rotating a phasor by 90 degree or pi over 2. Okay, so if you have any number, z, for example, you have this complex number here, and you multiply or you take its derivative with respect to theta, for example, and what you end up doing is shifting it by 90 degree. You take a second derivative and you're going to end up like right here, 180 degrees, because it's going to be like the derivative once and derivative second time, and take a third derivative if you want, and you're going to end up here, and you phase shift again. So if you phase shift 4 times 90 degrees, you've gone around the circle all the way 360 degrees. And you can sort of like, if you insist on saying, going back to the square root of minus 1, and I promise I'm probably not going to talk to you about square root of minus ones anymore. But if you insist looking at it that way, it just adds up because I being the square root of minus 1 times the square root of minus 1 is a minus 1. And you do it 4 times. So this is your 90 degree, 90 degree, 90 degree, 90 degree. And you see when you do it 4 times, 1, 2, 3, 4, you're back to the same spot like multiplying by 1. And sure enough, I times I is minus 1. I times I here is minus 1. Minus 1 times minus 1 is equal to 1. All right, so we've proven that. But again, don't want you to think about I as a square root of minus 1, but as a 90-degree phase shift. All right, let's use a couple of other examples. I've mentioned that anytime you see sine waves and cosines and all that, and you go into like anything more advanced in math, you drop those out. You just don't use them anymore because e exponent I theta is much friendlier, much nicer to use. And in fact, hidden in there is our sines and cosines, because if you remember, the coordinates are sines and cosines, right? So let's take an example. If you remember a little bit about your derivatives, so let's go back to that, first derivative, d over d theta or d over dx. So if you remember, the derivative of a sine is a cosine. And well, it turns out that the derivative of a sine is a sine that's shifted by 90 degrees. And you take this shifted 90 degrees, a cosine there, you take it, you pull it down there, and you do another derivative, and you get minus the sine of x, right? The derivative of cosine is minus sine. Now, minus sine of x is sine of shifted by another 90 degrees, so it's a sine, it's the inverse, right? You got this whatever, and you inverse it. The inverse of a sine is the same as shifting it by 180 degrees or by pi. And again, you take the minus sine here, right? And you take its derivative, and you end up with the cosine minus cosine of x, and this again is sine plus 270 degrees. And you do it again, and you're back up to sine right there. So what we've done was we've sort of like shifted by 90 degrees, shifted by 90 degrees, shifted by 90 degrees, and we did it like 4 times. And the 4 times we did it, we're back to sine of theta plus 2 pi is equal to sine of theta, right? But when you look at, you know, sine of x and you look at its transformation, it no longer in you if you don't use complex numbers, right, or e exponent I theta, for example, right, it no longer maps. It's not quite the same function. Remember, like I said, eigenfunctions. Well, a sine and a cosine, they're very similar, but this phase shift is just this annoyance. And if you had to deal in math using sine and cosine and you use like transformations, you'd always be stuck with like some kind of a phase shift, and things just don't work out so well. So again, I'll never show you sines and cosines anymore going forward, right? Because they're just not friendly. They're not easy to work with. They're not really eigenfunctions of first, second, third derivatives, and so on. And they don't just don't play very well. And that's why we're gonna kill them, right? So sine of theta is dead, or cosine of theta is the same thing as a sine, right? It's just shifted by 90 degrees. So this guy is dead, right? Forget it, right? Gone. And the new king is again e exponent I theta. We're back to e exponent I pi being just one example, right? And so e exponent I theta is new king, right? So that's what we're going to be using. Now, if you have a signal, right, and you have, let's say, a tone, a 440 hertz tone, everybody who does music has this little pitching fork, and you hit it, and it makes a little beep. Well, that little beep there is like some kind of a signal, and you'd be tempted to say, well, it's a sine wave. Yeah, sure enough, it's a sine wave. I'm not saying it's not a sine wave. What I'm saying is that we're not gonna like express it mathematically this way. We're gonna express it that way, right? This here is far more powerful. Now, if you have a wave, an ocean wave, or a quantum wave, and I'll get to waves into another video. If you have waves, then you'd be tempted in maybe high school to show it as a sign of some kind of a wave number over position and a frequency over time, but dead, dead, dead. You're not going to get anywhere with this. This is the way you want to do it, right? Okay, all right. So now let's revisit these linear transformation. Okay, so if you remember this, either this is a more generic linear transformation, and this could be like a sum of derivatives, right? So it could be the first derivative plus the second one plus third and so on. Now, remember that if you have a certain, it's linear, and what happens is if you have a certain eigenfunction, then you get the same function back. So if you have, let's say, a 440 hertz tone, and it would be expressed this way. This is the math expression of, let's say, a 440 hertz tone, as long as W1 is 440 hertz, and here's the wave, right? You can look at it on the oscilloscope, for example, and and then remember, it's e exponent I something is an eigenfunction of this transformation. So you're getting the same wave, except that it's amplified, right? See here, this is the amplitude here, right? And it's phase shifted. And so it's multiplied by something. So here's the eigenfunction means you're getting the same thing over, and the eigenvalue is the scaling factor. And that scaling factor is a complex number. And because it's a complex number, it happens to have an amplitude and a phase shift. So when you're putting a certain tone into the transformation, you're getting the same tone amplified and somewhat shifted in phase, right? If you're putting a second tone into it, higher frequency pitch, I don't know, maybe 1,000 hertz or something like that, and higher pitch, and that's why it's swinging up and down a little faster. Maybe this one here is like you're gonna get the same tone out, but maybe this one is sort of attenuated, right? Because the amplification factor could be smaller than one, right? So either you scale up or you scale down, but you scale, and that scaling is an eigenvalue, right? Big name for just simply saying that it's just, tones down, or and again, this is, you're getting that same sort of tone, but it's multiplied by a to a certain uh, scaling factor and a certain angle theta 2, and that's how you should think about this scaling factor. So because the transformation is linear, then if you combine the two tones, right, if you take the 440 hertz plus the 1000 hertz, you'll know how this is going to transform, because it's linear. It's the same thing as you know how much the price of an orange, you know the price of a banana, so you know the price of an orange and a banana. So here's this one transforms into this, and this one transforms into that, and the sum of these two will transform into the sum of these two, and that's how it works. So again, back to say that if the function is an eigenfunction, and functions of this type or this sort, e exponent I omega t, which is, think of it as a tone, is an eigenfunction, then it'll actually scale, and you'll get the same frequency on the output, but except it's going to be multiplied by what we call a phasor. So it's amplified by the amplitude of that z phasor, and then shifted by that angle right there. So amplified by and shifted. Okay. And if you have multiple tones, right? So if you have not just like a 440 and 1000 hertz and 2000 hertz, and if you combine a signal, a more complicated signal, made out of, like, I don't know, like 16 different tones, right? And then, so what you end up having is you end up having some kind of a signal that's the sum. This means just a sum, right? That's like a sum over different frequencies of all kinds of different tones. And all these different tones can have different amplitude, right? So you can put a signal together and say, I'm going to put a little bit of 440 hertz, add a little bit of 1000 hertz, and then you could add like different tones, and then depending on the amplitude of each one of them, then you're going to get a different. So this is here, this AK here is the amount of how much, and this is your tone at frequency WK, and this is the amplitude of that tone, and you just add them up, right? And how does that transform? Well, that transforms into the sum of these, phasors. So for each frequency, it has a certain frequency response, and the frequency response is in there. The amp so each frequency gets multiplied by a certain amplitude, or scales up a certain way or scales down, and we refer to this as this right here as a frequency response. So here's the tone. Here's how much of the tone is in the original. And when you transform this, you put it through the equalizer. This is how much each frequency gets amplified or gets like a shrunk down. So back to the equalizer. If now what I'm looking at is just all of these for different frequency. You look at all of the ZKs right there. And if you put the equalizer flat, right, if you were to dial this down to 1, then the frequency response would be these are all your tones and your different frequencies. And this is your low range, right? This is maybe, I don't know, 20 hertz to something like 200 hertz. This is like your mid kilohertz. This is like, I don't know, 5K or something like that. And if you put your equalizer flat, then you get, amplitude is going to be flat. If you boost up the bass, reduce the treble or whatever, so you may end up with a frequency response that looks like this, right? But keep in mind that this amplitude right there, this amplitude right here, this amplitude right here, is those ZKs right there. They're eigenvalues of different tones. Okay. All right. So far, so good. Now, so remember that, we have right here a signal, and what we're doing is we're adding a bunch of tones together, and each tone has a certain different amplitude. And I'm giving you that signal, and I'm like, hey, is there a way for you to somehow decompose this and figure out, if I give you like a sound, and figure out what is the frequency content? And what you could do is you could be wise and say, I'm going to go to the Radio Shack store and I'm going to buy a spectrum analyzer. I'm going to take this and I'm going to push this into the spectrum analyzer. And guess what? It's going to give me that the frequency content, which is like some kind of like as a frequency scale, and it tells you what these AKs are. So finding out the frequency content of these AKs, how do you do that? Well, turns out there's like a fairly simple rule to do this, right? So because remember, like this is a transformation here, and this is like sort of the frequency response. But then if you're looking at these AKs there, right? So you need to know what is the frequency content. So given an input function, and we call that a signal, how do you calculate this frequency content, right? How do you do that? Well, it's very simple. You look at how much the overall signal, right, the combination of all these tones, how does it project against a single tone? And you look and you say, all right, so I've got something, and I know there's like a 440 hertz in there, and you sort of multiply it by a 440 hertz signal, and what you'll get out of it is the content of the 440 hertz, and that's how it works. So this is the projection. That's how it's done. It's called a dot value. So think of this function as like some kind of a vector, and you multiply it by the tone itself, and you're going to get out this AK, right? There's another terminology. It's called the Dirac terminology, the bracket terminology, and that does the same thing, right? So just how much does this project? And if you want to write it into like some kind of a summation form, so the frequency content, AK right there, of a certain input signal is, sort of the sum of how much the signal project into these individual tones. And it turns out that this here, right, the frequency content is a Fourier transform. And all along when you're putting together a signal from a bunch of tones, right, you're adding a bunch of tones together, and this is the inverse Fourier transform. So there you have it. So you have on one side the inverse Fourier transform, which is a sum of all kinds of tones, right? So a little bit of 440, a little bit more of a, and that amount of every one of them, how much you could sort of figure it out by using a Fourier transform. If you look at these two functions, this is the inverse Fourier transform, and this is the Fourier transform. And again, our friend shows up right here. See here? Our little friend, E exponent I theta, is right there, and there he is again, right? So that's why it's very important. So let's get into like your Wi-Fi right now. Okay, so when you're actually transmitting 5G Wi-Fi or LTE, so what do you actually do? So you have all of these different tones. Remember, I said here's your 440 hertz, here's your 1000 hertz, here's your 1500 hertz, and so on. And you have all these tones, and you end up like adding 64 of them, right? And we call these tones subcarriers, right? We call them subcarriers, and they happen to be orthogonal. And I'm not going to get into that right now, but they're orthogonal, meaning that one they don't project into each other. So if you try to look at them, they sort of like a little bit like if you have something that's at a right angle, for example, what is the projection of this arrow and this one is zero? It's the same thing with these different tones. And how much of each one, each tonality that you put is these amplitude here, right? So this right here is the amount of 440 hertz, and that amount here is a complex number. Why? Because it's got an amplitude and a phase, right? Phase theta. So again, each one of these A value this is a complex plane, right? And here's the amplitude and here's the angle. And this point right there is a different amplitude and a different angle. This one right here is different, more or less same amplitude as this one, but look, it's 180 degrees, right? Compared to that one. And what you do is you say, all right, so in my complex plane, I'm going to allow like a sort of 16 points, and you have 1, 2, 3, 4 times 1, 2, 3, 4, and I'm going to represent each one of them has a different angle or amplitude, and each one of them has a different phase, right? And you could, if you only allow 16 different position. So 16A theta, 16 position, which are these points right there, we call that QAM 16 modulation, right? And QAM 16 means that it can be represented. 16 is 2 to the 4 is equal to 16, so you can, encapsulate 4 bits. So this could be, think of this as 0, 0, 0, 0, 0, 0, 0, 1, and so on. And what you end up doing is you end up putting your zeros and one data, and then you give it each one of them a certain angle and magnitude, and you multiply this by the subcarrier, and you add them all up right there. And that's what you transmit over the air. And you're transmitting that over the air. And this here happens to be the inverse Fourier transform. It's the sum of a number of different carriers multiplied by an amplitude and a phase. And it goes to this function right there. So here's my sum, right? Here's all the subcarriers. This is the frequency of the subcarriers. And this is the amplitude here. And these amplitudes there, right, encapsulate the 4 bits that I described. And you transmit that over the air. And what do you want to get back out on the other side? You want to get your data back out. And how do you get your data back out? Well, what you want is you want to figure out what all these A's are, because you have 4 bits in there, and you have 4 bits in here, and you have 4 bits in here if you use QAM 16. If you use QAM 1024, each one of these amplitude here encapsulates 10 bits, right? And you have 64 subcarriers right here. And then on the other side, what you do is you do a fast Fourier transform. You do a Fourier transform, and you're getting back your amplitudes, right? You're getting your amplitudes back. And then for each one of these amplitude, what you end up doing is you end up with either this phase and angle, and if you get this somewhere around here, phase and angle, then you know that this is a 0, 0, 0, 1, for example, right? Or you get your bits back. So bits into some kind of a phase and angle. So and then you modulate this by using an inverse Fourier transform or adding up all these tones, and you get on the other side and you use a Fourier transform to figure out what the tones are, right? So just note a few things here. That's kind of cool is that these amplitude are, again, A is a certain magnitude and an angle, right? So it's got a amplitude and angle, and this is your QAM modulation. And here's your little tones. Your subcarriers, again, are expressed, again, using E exponent something, right? Oh, I forgot the I right there, right? So we have somehow a combination of our friend, right? So E exponent I theta here shows up in as the eigenvalue, and also happens to be an eigen function, right? So the very, very powerful tool, e exponent I pi plus 1, back to that Euler identity, and showing you how it's used to actually do 5G modulation. And no, it's not going to kill you. Don't worry about it. It's just going to make your data go faster. So that's the end. My next video that I'm going to do is the basis of quantum mechanics, and I'll show you how to use this and derive the Schrodinger wave equation, right? So that was done like by Schrodinger back, what, in 19, I don't know, 20s or something like that. Thank you for watching.